How do you solve an exponential equation? Well, the answer is it depends. Suppose we had an exponential equation like this. 2 to the power of 3x plus 1 is equal to 32. Well, this is a little bit more straightforward because if we had something like this, we recognize that 32 can be rewritten in terms of 2. That is to say, we can rewrite 32 as 2 to the fifth power. And now this has the same base as our left side. We have 2 as our common base here, in which case we know then that 3x plus 1 must be equal to 5, in which case we could just set these equal to each other and then solve, right? We would say 3x then is equal to 4 and x is equal to 4/3, and that would be our answer. Now, unfortunately for us, sometimes, well, I don't want to say unfortunately, it opens up a new set of possibilities, but sometimes we're going to have problems where we cannot write the other side in terms of the same base. So take, for example, this problem here. So 2 to the power of 3x plus 1 minus 31. Well, if I want to go ahead and I isolate my exponent or isolate my power, move that 31 over to the other side, 31 cannot be rewritten as something in terms of a base 2. So what would we do then? Well, after we have isolated our power and we've tried to find the same base of both sides or rewrite each side so it has the same base, and that doesn't work, then we're going to have to take the logarithm of both sides. So that is to say, we can write this as the log of 2 to the power of 3x plus 1 is equal to the log of 31. Now, why do we do that? This allows us to use the log properties that we learned in the previous section to rewrite this. That is to say, the power, 3x plus 1 is the power of our argument 2. So we can take this and move it to the front and write it as a factor. So 3x plus 1 times log of 2 is equal to log 31. Now, I can rewrite this, and I'm going to actually make this a little bit smaller so I have a little bit more space to work with here. So let me just zoom in on this. So now I can write this as 3x plus 1 is equal to log of 31 over log 2. And we can continue to solve for x. So this would be, and this, by the way, we can rewrite as log base 2 of 31 if you'd like to. This is just using the change of base formula, the change of base. Although you could just leave it as log 31 over log 2, that's fine as well. But I'm just going to write this as log 2 of 31. And if I just continue to solve here, I know I'm bleeding into the next set of problems, but that's okay. That's log 2 of 31 minus 1. And then x then would be equal to log base 2 of 31 minus 1, all of this over 3. Now this is our exact answer here, and our approximate value is going to be approximately 1.32. There's our answer there. So just to recap, whenever we have an exponential equation where we are unable to change to the same base on both sides, then we have to take the logarithm of both sides. And then that allows us to use the log properties to finish solving. Okay. So I wanted to go through a couple of these practice problems here with you, just to give us a good sense of how to solve these exponential equations. So let me get that out of the way and let's just start diving right into them. Let's solve this equation here. So my goal is to try to isolate my exponent. So I'm going to use inverse operations to rewrite this. 11 plus 14 is going to be 25. E to the x is equal to 25 over 3. Now I'm going to take the natural log of both sides. Why did I choose the natural log? Well, honestly, you could take the same kind of log to both sides, but the natural log actually makes a lot of sense here because my base of my exponent is e. So if I take the natural log of both sides, we know that the property says natural log of e raised to some power is just going to be equal to that power. Again, review the properties on logarithms from my previous lesson if you need a recap on this, but now I can just say this is x, and this is the natural log of 25 over 3. This is my exact value, I should say, and this is approximately equal to 2.12. Okay, let's try another one. Let's go ahead and try this problem here now. Again, my goal is to try to isolate my exponent. So I'm going to write this as 6 times 2t plus 5, subtract 4 from both sides, which is 7. 2 raised to the power of t plus 5 is equal to 7 over 6. Now that I've isolated my exponent, I'm going to take the log of both sides. Let me actually move this over so I can just do that. Again, you could take any log of both sides, but I'm just going to take kind of similar to the last problem. I'm going to take log base 2 of both sides. Let me actually do this in each of these in a separate color so we can, oops, I kind of did that, but it's all right. So we can see what we did there. So why am I doing log base 2 of both sides? Well, again, log base 2 of the same base, or in this case 2, if my base and my argument are the same, then all of this is just simply equal to the power it's raised to. So this would be equal to t plus 5. Now I have log base 2 of 7 over 6. T then is equal to log base 2 of 7 over 6 minus 5. And this comes out to approximately negative 4.78. Okay, let's look at another type of problem, something like number 3 now. At first glance, you might try to subtract 12 from both sides, but you're going to get kind of stuck because you're going to notice that you have an e to the x in both of the remaining terms. So instead, what we can do here is we can actually try to solve this like it's a quadratic. And if you don't see it, perhaps me doing this will allow you to see it a little bit more easily. And if that still doesn't work for you, then go ahead and write something like a being equal to e to the x. In which case, this would be a squared minus 7a plus 12. And factor this quadratic here. This is a minus 4 times a plus 3. And now if I sub back in what a is equal to, this is e to the x minus 4 times e to the x plus 3. And honestly, you didn't have to define e to the x in terms of some other variable a. I often just see that it helps some students see the structure of the quadratic a little bit more easily. But if you wanted to just jump straight from here to here, then that's all good as well. So now I can say e to the x using the zero product property must be equal to 4. E to the x must be equal to negative 3. And if I take the natural log of both sides, which let me actually just do that, the natural log of both sides, x is equal to the natural log of 4. Same deal over here. X is equal to the natural log of negative 3. And you know what? I factored this incorrectly now that I'm looking at this here. My bad. This is minus 3, minus 3. That's 3. There's 3 there. And now we're good. No harm, no foul. There it is. As long as I caught it. Okay? All right. Let's try a problem here where you actually have to see how long it'll take for an account that pays 6.25% interest, which is pretty good. How long will it take for $1,000 to double? Well, for this, I'm going to set up A is equal to P times E to the RT power. Pause the video and see if you can try to plug in the appropriate parameters into this equation. Well, we start out with $1,000. Our rate is 0.0625 written in decimal form. And we're going to be solving for t. That's what we're trying to find. We're trying to see what t is. And we want to see how long it's going to take. What will t be in order for our final amount to be twice as much as what it was, which is 2,000. But if we look at this carefully, if I divide both sides by 1,000, it actually doesn't matter what our principal value is. That time that it takes for that value or our initial deposit to double will be the same, regardless of whether or not it's $1 or $1 million. So now that we have a basic exponential equation, we can solve by taking the natural log of both sides. We've done this enough times now. Hopefully it makes sense why I'm taking the natural log of both sides. Let me just continue this over here. The natural log of 2 is the numerator. The denominator, or let me just write this first. Since we took the natural log of that right side, we're going to get this. T is simply equal to the natural log of 2 over 0.0625. And if you told someone it's going to take natural log of 2 over 0.0625 years, they'd probably look at you like you were crazy. So we're just going to say it'll be a little more than 11 years. That's the approximate value. Okay. All right, let's finish this up with the last two problems on this page. Let's try number 5. Number 5, if we look at this carefully here, we notice that there are some common factors. We've got that common set of common factors. I also see that there's an x in both of those terms. So if I factor all those out, I've got an x that I can factor out. Let me actually highlight that. I also have an e to the negative x that I can factor out. And I also have this left over, negative x plus 2 is equal to 0. Again, using the zero product property, let's set each of these equal to 0. X is equal to 0. There's one of my solutions. E to the negative x, if I set that equal to 0, wait, pause, think about this for a second. There is no way that e to the negative x could ever be equal to 0. There's nothing I can plug in for x that would ever cause my output to be equal to 0. So I don't have to really worry about this. Negative x plus 2, on the other hand, I do want to use. Negative x is equal to negative 2. That means x is equal to positive 2. There's my solution there. And then finally, for number 6, let's take a look at this one. For number 6 here, I notice that both sides have different bases. That's not anything new, but I do know I'm going to want to take the log of both sides. Doesn't matter which log we do. I'm just going to say log base 2 of both sides. And that's only going to help me on one of the two sides, but hey, one is better than nothing. I know all of this then is going to be equal to x minus 5, because log base 2 of some argument, that's the same as our base. It's just simply this power, so that's x minus 5. This over here, now that I have this, I can move that power over to the front using the log properties and say that this is 2x plus 7 times log base 2 of 3. Now, we still have an x on two different sides of the equation. So what we're going to do is we are going to distribute this log base 2 of 3 to both terms inside here. That is to say, this is going to look like 2x log base 2 of 3 plus 7 log base 2 of 3. Now, you might be asking yourself why we're allowed to do this. Remember that log base 2 of 3, let me just highlight this. Log base 2 of 3, this is simply some constant. It is a value. It is a numeric value. It's an irrational number, but that's no different from us distributing something like pi, which is an irrational number written as this constant. So I'm allowed to distribute this here because it's just a numeric value. Now I'm going to move all my x terms over to one side, so x minus 2x log base 2 of 3, and my non-x terms over to the same side. From here, it's just basic algebra. We're going to factor out our common factor. So we got 1 minus 2 log base 2 of 3 is equal to 5 plus 7 log base 2 of 3. And then finally, 5 plus 7 log base 2 of 3 over 1 minus 2 log base 2 of 3. Okay? Well, hopefully I didn't rush through that too much and that makes sense. And hopefully this video helped out in recapping the processes for solving an exponential equation.